Swayam Prabha. Digital India. Educated India.
Welcome to the 6th lecture in the course Variational Methods in Mechanics and Design. In the last 2 lectures we said it was a detour, and so is today's lecture. It is also a small detour, but it is important to appreciate calculus of variation. So, we are talking about the finite variable optimization. First we discussed unconstrained in lecture number 4, and then constrained, where we discussed the KKT conditions, constraint minimization, lecture number 5. Today we are going to talk about the sufficient conditions for finite variable constraint minimization. Here is the outline of the lecture. We will first talk about what are called feasible perturbations. When you have constraints, you need to satisfy them when you perturb to see if a point is a minimum or not. For that, for establish sufficient conditions, we have to take the second order term in the Taylor series approximation of the n variable function. Using that, we will establish sufficient conditions and then introduce a term that is not often found in optimization books called bordered Hessian. Some good books do talk about it, many of them do not. This concept of bordered Hessian, which is very important to know if a given minimum is sufficient or not to do it easily. Okay. What we will learn in this lecture will be how to interpret the feasible perturbations around a local minimum. Okay. Then we talk about this Hessian's positive definiteness being more than what is required, like it is an overkill. That is where this bordered Hessian concept comes, and we will understand its significance. And we will also learn how to check if a given minimum for a constrained optimization satisfies sufficient conditions or not. We will get a technique to verify that. So, first let us recapitulate this KKT conditions, that is Karush-Kuhn-Tucker conditions for constraint minimization. So, for a problem such as the one shown here, minimize f of x subject to equality constraints, there will be m of them. This is a scalar, f of x is a scalar, h of x, when we put in bold letters we mean that it is a vector or an array. So, the h1, h2, hm are there, that is equal to 0, and then inequality constraint g of x less than or equal to 0, again we have g1, g2 up to p. When we have that, we wrote the KKT conditions here, Karush-Kuhn-Tucker conditions. The first one, again to recap, says that the gradient of the objective function is a linear combination of the gradients of the constraints, both equality constraints and inequality constraints. And then such a point x star which satisfies this first of KKT conditions should also be feasible, meaning that it should satisfy the equality constraints and the inequality constraints. Here when I put k, the k goes from 1 to p, and then we have these mu k, g k evaluated at that point x star, which we believe is a minimum. Those are called complementarity conditions. And then we also discussed that this mu corresponding multiplier corresponding to the inequality constraints should be non-negative. When it is 0, corresponding constraint is inactive. When it is not 0, the corresponding constraint is active, meaning it is strictly equal to 0. We noted that there could be a special condition where mu k and g k both can be 0, but what it says is that it is greater than or equal to 0, it cannot be negative. Okay, these are the things that one should note, that KKT conditions say that the gradient of the objective function can be expressed as a linear combination of the gradients of the inequality constraints. Okay. And then Lagrange multipliers of the inequality constraints cannot be negative, they have to be positive or 0. whereas those correspond to the equality constraints can be of either sign, they can be plus or minus. Okay. That is why we use a different symbol lambda and mu. Mu has to be strictly non-negative, whereas lambda can be negative or positive or 0. Complementarity conditions, these are the ones which tell you how to decide whether a given constraint is active or inactive. Okay. Now, to understand KKT conditions, let us flip it. If you see in the previous slide, we were saying minimize with respect to x, this objective function. Now, let us say we want to maximize it, maximize f of x with respect to x. How do the KKT conditions change? The change is shown here, right. So, here previously we said mu k should be non-negative. Now, we are saying they should be non-positive, because they can, this shows that less than or equal to 0, it can be less than 0, which is negative, or equal to 0. Okay, that is a change it comes about. Why does this change come about? The change comes about because we are maximizing. If you look back at the previous lecture where we argued why there is a restriction on the sign of Lagrange multiplier corresponding to the inequality constraint, you would recall that if you take the first order term, that is gradient of f times delta x, that is perturbation around the minimum x star, that we want it to be positive when f of x star to be a minimum, whereas when you are maximizing we want this change, that is gradient of f times delta x star, that has to be less than, that is negative, in order to have f of x star to be the local maximum. So, that change brings about this change, because again we had said inequality constraints, when I perturb it, that additional change should be negative. This is negative, that is negative. When you look at this gradient of the objective function and this gradient of the inequality constraint, then both are positive. Then this, if I multiply this by delta x star, right, without mu of course, then we see that these two should be equal to 0. In that case, this mu multiplies this one, that has to be less than or equal to 0, right. Just recall the same argument, when I flip to maximum, this should become less than or equal to 0, because different books have different conventions, some of them minimize, some of them maximize, and some of them may put this inequality constraints, instead of less than or equal to, they may put greater than or equal to. If we do that, what happens, we will see in the next slide. So, notice the sign change of the Lagrange multiplier correspond to the inequality constraints. Okay. Now, they should be non-positive. Now, if I say max, this we have. Okay. Now, what if I change the sign of the inequality constraint here, greater than or equal to 0 instead of less than or equal to 0, that also flips it to be less than or equal to 0, because now after perturbation this should be positive, the perturbed value, that is gradient of g times delta x star should be positive. The same thing with corresponding first order term to f of x, then both of them should sum together to 0. So, the negativity of the Lagrange multiplier will take care of it. Okay. Now, what if we make both changes, that is we are maximizing and the inequality sign is greater than or equal to, then it will remain to be again non-negative. So, once you understand these 4 variants, original form that we wrote, and then max, the third one greater than or equal to for the inequality constraint, and the fourth one which is on this slide where you are maximizing and inequality constraint is posed as greater than or equal to. Okay. So, you have to be careful about how the problem is written, accordingly you write the restriction on the Lagrange multiplier corresponding to the inequality constraints. Now, let us move to sufficient conditions, which is the main point of today's lecture. And for constraint problem, there are no constraints, this is what we said should be true. This is a second order term in the Taylor series approximation, because for a local minimum first order term is 0, right. And now second order term has to be positive in order for f of x star to be a local minimum. This is a second order term written in the matrix form, delta x star, delta y star. If I take a 2 variable problem, these are the perturbations from x star and y star, and the row vector form of that, column vector here in the 2 by 2 matrix, which we call the Hessian, denoted by this H, x star y star, that is evaluated at the putative minimum x star y star, this should be greater than 0 for any perturbation. If that is what this H has as its property, then we say that particular point, that is x star y star, is a local minimum, and that satisfies sufficient condition. Okay. So, this H is the Hessian to be positive definite, that is what we want, that is the nature of positive definite matrices. Whatever, if you take any vector, you post multiply by the column and then pre multiply by the row, whatever you get should be greater than or equal to 0. This half is just there because quadratic term has half, otherwise half has no significance. Okay. Now, how do you check this for the unconstrained problems that H is positive definite? There are many ways, there are 3 ways. The easiest is eigenvalues. If all eigenvalues are positive, such a matrix is said to be positive definite, and that will satisfy this property. Other way of doing this is to check the principal minors of the matrix and ensure that they are all positive. Principal minors are, the largest principal minor is the determinant itself, that is you take the entire matrix, take determinant. The one before that will have the first row and first column removed, and it goes like that. Okay. So, first row, second row, first row, first column, second column, if you keep on removing it, we get principal minors. All of them have to be positive, or the pivots, so called pivots that come about when you take the matrix and reduce to this row reduced echelon form. If all pivots are positive, that also is a test for positive definiteness. The latter two, the principal minors and pivots, are not used that often, because now we have very powerful numerical analysis software which will give you all the eigenvalues. So, that is the best one. If all eigenvalues are positive, then you have positive definite matrix, which is sufficient condition for a problem without constraint, that is unconstrained minimization. Now, if you consider a problem which is constrained, whose necessary conditions, the so called Karush-Kuntakar conditions that we discussed in the last lecture, a little bit today, what about the sufficiency of such a problem? Okay. First of all, if we talk about sufficiency, we have a point which is told to us to be a minimum. Now, we want to check. So, we want to move around, perturb in the vicinity of that point, and then show that any other point in the vicinity has a higher value of objective function compared to value at that point. But then when you have constraints, which is the case with constraint optimization, the search, the vicinity that you look for, if there is any point that has higher value than, lower value than the function that the point that where you are, which is supposed to be minimum, then you cannot search everywhere in the vicinity, but you have to search in the constrained subspace. So, let me get a pen. Okay. So, the constrained subspace, right. So, that is the focus here. We have to talk about constrained subspace. That is, if I have a point, let us say I take a 2 variable problem, 3 variable problem. If I have a point somewhere, I look around that point, little space around it. When you do not have constraints, you can search everywhere, but now when there are constraints, a part of it may not be allowed, right, that may not be allowed, then you have to search only in the vicinity here, that is what will be constrained subspace. Okay. So, for sufficiency conditions, we need to consider only what are called feasible perturbations. Feasible point is the point that satisfies the constraints, both equality and inequalities. Now, when you say feasible perturbations, those perturbations, if this is the point, I can check here, 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 if those are allowed, right. So, let me change the color. Yeah, if this is the point, I can take here, 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 but not here, because that is not feasible, because that does not satisfy the constraints. We say that this constraint says that it cannot be below that, right. So, that is what we mean by feasible perturbations. So, if we have m equality constraints and some active inequalities. Inactive inequalities are inactive, so you can throw them away, but there could be some active inequalities, meaning those where Gk, if I call k as an index for this, should be strictly equal to 0 rather than being less than or equal to. So, there are active inequality constraints. So, once you have an active inequality constraint, it is same as inequality constraints, and if these constraints are linearly independent, which is a requirement that we call constraint qualification. Okay. If we have such a thing, then the perturbations should be chosen such a way that they lie on a hypersurface, okay, of dimension n minus m, because you have n variables and there are m equality constraints or active inequality constraints. So, the perturbation that we make will satisfy these little perturbations of the active inequalities and the equality constraints, and hence we will have freedom to choose only n minus m perturbations. Okay. So, that is mathematically shown like this, where the constraint subspace, which is this S here, is such that all x star or delta x star, whichever way you take, they have to satisfy the constraints h x star, and I must also add G active x star equal to 0. I am putting over bar because there could be more than one inequality constraints. A here denotes active. Okay. Active inequalities are equal to equality constraints. Such a hypersurface, hyperspace or constraint subspace is where we need to check in order to see if the point has the lowest value in the vicinity, because we only talk about local constraint minimum. Okay. How do we do that? So, if you look at it graphically, consider that a 2 variable problem where you have h1 is a function of x y and then h2 is a function of x y equal to 0. So, we have two equality constraints. That means that there is a surface h1. If I put x y as the plane and z, I take this h1, then I get a surface. Corresponding to h1 I get a surface, corresponding to h2 I get a surface, right. So, these things will be there at some value. You have h1 equal to 0, h2 equal to 0. Then since both constraints have to be satisfied, then we get this thing which is intersection of those two. That will be the hypersurface we talk. We call it a surface, here I am showing it like a curve. So, if we have in let us say 4 dimensions h1 equal to 0 will be like a surface, okay, and h2 will also be a surface, their intersection will be a curve. Only there I can search, right. That is what we are showing, that is the hypersurface which satisfies this. Again when I say H, it also includes the active inequalities, which means that when we perturb and look at this term, which is what we are seeing here on this slide for the objective function. Okay. So, we have to consider the perturbation, first order perturbation, which is this first order term in the expansion of the function delta x delta f, that is gradient of f multiplied by perturbation delta x star, which includes the independent perturbations and dependent perturbations. In the last lecture we were looking at this x being subdivided into d and s. D are decision variables, you are free to choose, and s are the solution variables which you cannot choose because the constraints determine that. So, we have the first term where we are taking with respect to the solution variables, and then second term with respect to the decision variables. Since equality constraints have to be satisfied after perturbation, we can express this delta S star, that is solution variable perturbations, in terms of decision variable perturbations. Okay. When we substitute this delta S star for this delta S star for this over there, we get something like this, where we have delta D star are the decision variables. That is all we can change, all right. So, now we want to see how to establish sufficiency. For that we had thought of this function z think of that as a new function that depends on n minus m variables, because original function was dependent on n variables, but then we have m equalities or active inequalities. Now those m variables are taken out, we are left with n minus m variables. Those n minus variables, we can talk about this as a gradient of the new function z. Okay. That z, dou z by dou d if I take, that will have basically z is nothing but f, dou f by dou s by dou d plus dou f by dou d, which is what we have as two terms, because the z essentially depends on d and s, but s is dependent on d, and that is where this comes about. Okay. What is dou s by dou d? It comes from here, right. So, whatever is seen here is exactly what we have there. Okay. I put a delta s star equal to something times delta d star, that essentially means that dou s by dou d, that the partial derivative of the solution variables with respect to decision variables is given by this quantity, and that is what we need to put in here. Okay. Then we get this gradient, and we can take another derivative of this quantity to get the Hessian equivalent of the constrained problem. See, if you remember, for the unconstrained problem we were taking the Hessian of the f directly, but now we are not supposed to do that. We need to look at the constrained one after taking out the dependent variables based on the equality constraints and active inequalities. Okay. So, we start with this dou z by dou d, the new function which is n minus m variables. Okay. We substitute this over here and compute this dou z by dou d, and then take another derivative of that. Okay. So, we are taking this which comes from the previous slide. Now, we need to differentiate this first order term of this new function z one more time to get the second one. Okay. That is the form we are looking at, that should be positive, right. This should be positive definiteness, positive definite. Okay. When you say positive for matrices, it is not like a matrix is positive when all its entries are positive, that is not at all correct. What we say is a positive matrix or positive definite matrix is if you get a quadratic form with any vector, it should be greater than 0, that is what we had in the previous slides. That is what we need to compute for this quantity. So, now we are taking derivative of this dou z by dou d one more time. So, again we have the chain rule here, because some variables depend on the others, d by dd of the quantity here plus d by d of that quantity over there. Okay. We will take derivative of this thing with respect to d, that is what we have done in the first line, okay, that is here. Now, we need to expand. So, over here dou f by dou s transpose is there, d by d of this, and then d by dd of this, basically product rule. We have a product, that is two terms here, 1 and 2, and we are taking derivative one at a time to get this, and then same thing here. So, we have only one term over here, but then this dou f by dou d with respect to d first. So, it becomes second derivative with respect to x. The same thing we have to do here, because when you take with respect to d, we will take with respect to s, and then we have also with respect to d. No, this is first with respect to d here, and then second time with respect to s, and that process we also need to put ds by dd as well, because the solution is dependent on the decision variables. Okay. This is expansion, even if you do not see it right away, if you sit down and think about it, you will know how these steps come about. It is just a plain old differentiation, no tricks involved here. Okay. Now, we have basically d square z by dd square from the previous slide. This lengthy one, that is this lengthy one is reproduced here, and we are writing in the matrix form. It is only rearranging these things, there is no other trick here. It is just a matrix form of the scalar expression into this form, right. If you look at this now, what are all the things that we can compute? We already know this because we had used that earlier, and we know how to get this, that is just differentiating the objective function twice with respect to Asian variables. We can do this, we can do this, we can do this, and as I said, we already have this and we have this. What we do not have is this. We do not know dou square d square s by dd square. We do not know how the solution variable second derivative with respect to Asian variables is. In order to compute this, we do exactly the same thing for the constraints, right. So, we take second order term of the constraint and we say that should be equal to 0. Then we get this quantity that we do not know, right. That is what we will do next, okay, using the fact that h equal to 0 to second order, because when you talk about sufficiency, you have to consider the term in Taylor series up to second order. So, when you have constraints, you want to be 0 after perturbation, constraint should be 0 up to second order. Anyway, first 0th order term is satisfied because it is a feasible point, and first order term, it will be part of KKT condition, that will be there. Now, when you perturb it, you have to make sure that the h remains 0 after the perturbation. So, whatever we did for the objective function, now we are showing it for the equality constraints as well. Okay. Now, this should be equal to 0. Okay. That gives us a way to compute our unknown thing, d square s by dd square will become inverse of this quantity which is over here, and then the rest of it, that is all that is here is seen over there. Okay. Now, we got this. Now, we go back and substitute this thing, that is substitute for this in the second order expansion of our z. Z is basically the new function that we imagine, which takes care of the active inequalities and equality constraints. Okay. Now, we substitute and go back, look at this d square z by dd square, then we get something like this, right. So, we have plus this whole thing that we have as a second term is that d square s by dd square, okay, that we have this long one. Now, we also recall this fact, how we define the Lagrange multiplier. It is basically the sensitivity, negative of the sensitivity of the objective function to the sensitivity in the constraint, okay. That is what is lambda. When you recognize this and this together, so these two terms will become lambda, right, including the negative sign. So, negative sign is also here, okay. So, we get that d square z by dd square in this form, where we note that this Lagrangian is nothing but f plus lambda h. So, whatever, if you go back to the previous slide, whatever was happening to f in the first term is also happening to h in the second term, because this whole thing is lambda. Okay. So, we can say rest of it is similar, only f here becomes lambda times h. Okay. So, that is how we get f plus lambda h in this manner, right. Now, again notice that this z, which is dependent on n minus m variables, is like unconstrained function. So, for the sufficiency for that such a thing is that should be positive definite. In other words, whatever delta d star that I take, that is Asian variable perturbations, and the transpose of it get a scalar that has to be greater than 0, that is positive definite, greater than 0 strictly positive definite. If it is greater than equal to 0, positive semi definite, and all that we had discussed earlier in lecture number 5 or lecture number 4, all that applies to this z as well. So, this is the sufficiency condition, but then which delta d stars do you take, the question will arise, right. So, for that we have to go back and look at the fact that whatever we have taken delta s star, delta d star partitioning, that does not really matter. If you now look at this delta, if you take this quantity which we say should be greater than 0, we expand that, that the z part of it, what we have this L that we derived earlier, okay, in terms of D's as well as this S's, because that is the expression we had for this thing d square z by dt square in terms of L, we are substituting everywhere long term, right, first, second and third term and fourth term. And then note a few things that delta S star is nothing but ds by dd times delta d star, and transpose, if you put all of that and do a little bit more of the substitutions into this. Okay. Again you have to pause and look at every term to understand if you do not see it right away. So, if we arrange this long expression where we substitute in terms of delta d star delta S star, you get something like this. Okay. So, we have the perturbations delta S star delta d star, which is nothing but delta x star. Now, which way you partition does not matter now because they came together, and what we should notice is this matrix, that is dou square L by dou d square, dou square L by dou d dou s and all that. Okay. This is nothing but basically Hessian with all of them, because d and s whichever you part does not matter, it basically becomes the Hessian of the Lagrangian. So, notice that it is L, not objective function but Lagrangian, that should be greater than 0 because that should be satisfied. But again remember that these cannot be arbitrary, only delta d star, that is only n minus m of those can be arbitrary, other ones get depend on those. So, we have this constraint that equality constraint gradient and active inequality constraint gradient should be equal to 0. We do not want this delta x star to be arbitrary, which was the case in the with the minimization, unconstrained minimization, but now constrained minimization, these cannot be arbitrarily chosen, that to satisfy this. Okay. How do we do that is the question. So, when we look at H, what H? This is the Hessian of the Lagrangian. When you say H here, this H is Hessian of the Lagrangian. Okay. That being positive definite is whatever we are saying along with this constraint, okay, that is those perturbation that satisfies the equality constraints, first order term being equal to 0 and active inequalities. This is less stringent than asking generally this Hessian of the Lagrangian to be positive definite. So, if you say this should be positive definite, you are asking for more, that is an overkill. This is while okay, but we can go for something that is less stringent than that, which we discuss in the continuing lecture. Thank you.